Okay. All right. So hi again. So this is my second lecture this morning, and this is right before the lunch. So it's a hungry session, but I hope you can keep your attention. So well, actually after the first lecture of mine, some organizers told me that you may be scared by the asking for me to ask in the presentation and discussion section. I asked for the using the list of the participants and asked randomly, but that in that way, some very young people may be scared because you don't know much about it, and so this may not be a good idea. And I also found that it is not a good idea if some people are scared by that, because those people may go out of the lecture room when my lecture started. So please stay here. No worry. So I will just ask for the volunteers in the presentation section. So no worry, please stay here. So anyway, so I want to start my second lecture. So the aim of this section, Galaxy Formation 1, is to understand the basic theoretical framework of the galaxy formation and with the associated Lyman-alpha emission, and identifying the advantage and the difficulties of the theoretical modeling. So actually, I'm an observer, as many of you know, so I'm not the right person to talk about the theoretical frameworks. And I think well, how many theorists are in here? So please raise your hand. So okay, 2, 4, 5. Okay, not many. Okay, thank you. So about 10 people. And observers? Yes, majority. Thank you. So I feel good. So because I brought the very elementary material, which is for the level of the senior student and also the first year graduate student level theoretical framework thing. But I think that is very important for you observers to know. So I just go through the very basic theoretical thing for spending about 10 to 20 minutes, and then move on to the other observation things. And so here is the other advance notice. So I show the questions I will ask later. So the question is, what is the most challenging component for modeling Lyman-alpha emitters and phi? Okay. So especially for theorists, my talk is maybe nothing. So please think about what is the most challenging thing and important thing for the modeling Lyman-alpha emitters. It is very, very difficult, I think. Okay. So having this, let's go through the contents. So the basic picture of the galaxy formation is something like this. 2 stages. Starting from the initial density fluctuations, and the structure grows by the gravity, and having the dark matter halos, virialized dark matter, and then you have the mixture of the gas and dark matter in it. This is the first process. And then the second process is the star formation is triggered after the gas is cooled down by radiative cooling, and dense gas is formed. Gas clouds form at the center, then you get the stars. So the basic idea of the galaxy formation is these 2 steps. One is the dark matter halo formation and the star formation. So I go through the first component of the galaxy formation. So as many of you know, this is the simple n-body simulation. Oh, oops, sorry. Simulation, collisionless, dark matter particles are used, and just they interact by the gravity. So this is the result of the Millennium simulations, and as you can see from high Z to low Z, the dark matter particles get together by the gravity, and now you see some of the clumps here, which are dark halos, virialized dark matter, and also at the center you get the big dark halo, which eventually becomes the cluster, the dark matter halo of the cluster. So in this way, n-body simulations nicely predicts the structure of the universe, and the dark matter dominates the matter. So the cosmic structure is very well defined by such n-body simulations. So even recent studies of using the supercomputing technology, now the computers can resolve dark halos down to say 10 to the 7th solar mass, or in other words, close to the mini halos, or like very low mass halos. So probably the structure formation covers most of the other structure in the universe within the cosmological scale simulations. So there are no the unknowns. No, how do you say, difficult problems of such n-body simulations, and any n-body simulations show the very similar results. So we think that we understand this part of the structure formation made of the dark matter and dark matter halos. And also the other great thing of the structure formation is that you can approximate such a structure formation using the analytic formula, and such as named the Press-Schechter function. And the idea of the Press-Schechter function is that you start with the initial perturbation, and then it grows, and assuming the spherical collapse model, you can identify the critical density, over density, how large overdensity can make the dark matter halos, collapsed structure. So such a, the threshold can be easily calculated, analytically. So that is the delta is the 1.69. So this is the within the linear regime. So it is the 1.69, and if you allow the how to say, collapse halo, then this density should be around 200. But in a linear regime, this is the 1.69. So if you plug this in, then you can get the mass function. So how much the number density as a function of the mass for each redshift, from redshift high redshift to low redshift. So this functional form is called the Press-Schechter function, and the basic structure of the Press-Schechter function is the number density of the dark matter halo is proportional to the exponential term of the exponential term times the power law mass. So this structure is very related to the observations. In other words, luminosity functions. So okay. Sorry, I thought okay. So well, of course, there are many modifications of such a Press-Schechter function. Press-Schechter function is just approximation with a crude spherical collapse model and very simplification. However, if you compare the result of the Press-Schechter function, this is shown with the blue dotted lines, and these red circles with the line show the result of the numerical simulations, and it really approximates the numerical simulation very well. But well, you may worry that this difference. So then people use people define the modified Press-Schechter function to try to fit to the result of the real n-body simulation result, having some more parameter sets, and such a modified Press-Schechter functions are, very popular, such as the made by the Shess and Tolman 1999 classically, but recently Tinker et al. 2008. But these studies, have the normalization, calibration down to the low redshift. So recently, Beruzzi et al. Shows such a modified, Press-Schechter beyond redshift 2.5. So this is very useful way. You never to run the n-body simulations, but I easily get the mass function to compare your observations. And so why I talked about the Press-Schechter function is this is very related to the luminosity function. So this is the galaxy luminosity function. So galaxy luminosity function is the number density of the galaxies as a function of the magnitude or luminosity, right? So, but well, halo mass function is the number density as a function of the mass. And of course, galaxies are formed within the dark halos, so they should have close correlation and similar, functional form is expected. So, well, the difference is the mass and the luminosity between these two functions. So if you assume the mass to luminosity ratio, say constant mass to luminosity ratio, then you can easily, assume, you can easily get the functional form of the luminosity function. Of course, the universe is not that simple. So, Schechter 1976 parameterized this Press-Schechter function using the three parameters of the power law slope alpha and the normalization of the number density phi star or n star, and also the typical characteristic luminosity of the L star. So then people use this Schechter function to represent, to understand the luminosity function of the galaxies. So now we know the dark matter, and dark matter halos and the structure formation is pretty well understood. Let's look at the star formation component here. So the key component is first the radiative cooling that makes the dense cold gas clouds needed for star formation. So this is the classic cooling function. I think many of you have already seen it in your classes in the university. But this shows the cooling function, lambda, as a function of the virial temperature. So lambda is defined by the cooling rate divided by the matter square of the matter density. And so this shows how easily you can get the cooling. So the upper part shows the faster cooling, and for the no metal gas clouds, you have the two peaks which represent the hydrogen and the helium recombination energy. And also if you have some metals in the gas clouds, then these gas metals allow more transitions. So easier, faster cooling, larger cooling function is expected. Especially this is the solar metallicity, so it is pretty, fast, cooling is expected. So well, then you can just calculate the cooling time, which is the total kinetic energy divided by the cooling rate. So if you plug in the virial temperature by the virial theorem, then you get this cooling time is a function of the temperature, virial temperature, and the density. And similarly, you can calculate very crude, free fall time using this. Then this is a function of the number density. So if you plug in these two into one diagram, then you get the cooling diagram, which is very famous. So this y-axis shows the number density, and this is the virial temperature. And if you can correlate, these two quantities of the cooling time and the free fall time, okay. So if cooling time is the shorter than free fall time, then the gas never feels the pressure. So you can easily get the collapsed gas. So it is very busy plot, but please look at this thick line, which is for the thick line. So beyond this thick line, you see the cooling time is shorter than the free fall time. So you can easily get the dense clouds. So and you can calculate the mass of the halo by this, and as you can see, 10 to the 12. It allows large parameter space of the temperature and the number density, so gas density, so mass density. So in other words, you have quite efficient star formation for the halos of the 10 to the 12 solar mass. And for the other very massive one, well, it's too hot. So and also the other low mass halos, well, it is also more difficult to get the stars. So in this way, you have very complicated thing. And also another difficulty for the gas cooling and triggering the star formation is feedback. In many conferences you hear about the feedback. Well, the original idea of the feedback is if you compare observed galaxy luminosity function with the dark matter, halo mass function, the shape is different. So this dotted line is the dark matter halo mass function. So the real galaxy function shape is something like this. And you have suppressed number density of the galaxies in the massive end, and you have the suppressed number density in the low mass end. So these differences are thought to be made by the feedback effects of the AGN heating and supernova heating and so on. So how you can quantify this feedback effect? It is also a very difficult thing, but people define the mass loading factor, which is the mass outflow rate divided by the star formation here. So in other words, how much gas can go out with given the star forming activities. And well, it's derived by the observationally and from the simulations, but it's poorly determined. Here, I show the mass loading factor as a function of the halo mass predicted by numerical simulations. And there is the two major sequence of the mass loading factor depending on the two major mechanisms, physical mechanisms. And for the low mass end, it's quite steep. So this is made by the thermal energy inputs from supernovae and the young stars and so on. And this is steep because this is driven by the energy. In other words, square of the velocity, it's proportional to the square of the circular velocity of the halo. So it's steep. But for the high mass end, this relation is quite flat, and this component is called the momentum-driven feedback. So momentum-driven feedback is given by the kinetic energies of the AGN and stellar wind. So in other words, it's proportional to the velocity. So this is halo mass, but you can derive this with the halo circular velocity. But well, it's proportional to the 1 over b, the circular velocity. So it's steeper. So there are the two sequences, and now we are talking about the Lyman-alpha emitters. So where is the Lyman-alpha emitters? So typical Lyman-alpha emitters having the dark matter halos of the 10 to the 10th to 10 to the 11th. So mostly, they are sitting in the momentum-driven, feedback regime. So, so in other words, important thing is that not only the you may worry not only the supernovae or star formation, but also probably the AGN activities as well. So next difficulty of star formation is the possible existence of the cold accretion. And well, I think many of you have already known, from the early 2000 numerical simulations shows the cold accretion or cold stream. So the idea is that the cold gas, well, it's not very cold, but 10 to the 4th Kelvin gas is falling into the halos through the filaments of the large-scale structures like this. And the gas density is high enough, like 1 per cc. So they are very dense, so they can penetrate into the center of the dark matter halo, and they collide at the center. So if you have this thing, then you have the very dense gas. So you can produce a lot of stars. So this idea is very useful, because at redshift 2, well, this is the argument of the arbitrary decays, classic paper. But there are so many high star forming galaxies, like the 100 solar mass per year or so. So like the LB Lyman break galaxies or SMGs and so on. So they do not show, many of them do not show the merger signatures. So, and then question is that how you can maintain such a strong starburst with no merger effect. So then probably the idea is if you think these populations are just made by the cold accretion or cold stream, then they can have such a strong starburst with no significant clumpy structures similar to the other mergers. So the cold accretion thing is still open question observationally and even theoretically. And from observations, many people, like from the beginning of 2010s, people tried to find the cold accretion. And one of the other famous one is the result of the other Keck studies, looking at the Lyman break galaxies at redshift 2 and with the Keck Ellis spectrograph, and to measure the low ionization interstellar medium absorption lines. Please look at so this is the velocity, and this 0 is the systemic velocity of the galaxies defined by the H-alpha emission. In other words, velocity of H2 regions. So then, if you look at the interstellar absorption lines, low ionization absorption lines, which should be similar to the one of the cold accretion, then you have the peak of the velocity at around minus 200 kilometers per second. In other words, absorption line is blue shifted. So blue shifted meaning the gas is outflowing, not inflowing. But you recognize that there are some possible outflowing cold gas. But according to the other cold accretion studies, like greater than 300 kilometers per second, accretion gas is expected, but nothing in their sample. So the reason is not clear, but some theoretical studies indicate that cold accretion can be found. It's very filamentary, and the covering fraction is so small. So if your observation is luckily in the direction of the cold stream, then you can identify such a high velocity accreting gas. But filling factor, covering fraction is so small, like 1% level. So probably some people say this kind of the cold accretion is very difficult to identify because the covering fraction is small. So now I have talked about the many difficulties of the star formation thing, but for modeling, for our understanding, some people can make the shortcut to model the star formation activities. We see there are so many difficulties, so many parameters, including feedback, possible cold accretion, contribution, and so on. But some modelers use the empirical relation of between the gas and the star formation rate. So such as the Kennicutt-Schmidt law. So Kennicutt-Schmidt law is, as you know, the surface gas density as a function of the surface star formation rate. It has the strong correlation between two quantities. So these are known for the local galaxies. So from simulations, well, if you can put the some gas particles in a SPH simulation, such as, then you can get surface gas density easily, and then you can just plug in the star formation rate following this relation. So I think this is totally fine and representing the real universe. But so in this way, people try to, how do you say, remove the uncertainties of the star formation processes. But of course, there are no understanding of the star forming activities if you use this kind of empirical relation. So, well, as I have told you, galaxy formation is made of the two components. One is the structure formation, and the other is the star formation thing. And the structure formation thing is well understood, but star formation includes a lot of difficulties, many parameters, quite challenging, like gas cooling, feedback, so depending on metallicity outflow and so on, and cold accretion and so on. So then I would like to clarify that the role of the observations, Lyman-alpha emitter observations, are the identifying key quantities that constrain the major parameters of the star forming activities. Then that really nicely constrain on the star forming process and try to help the modelers to reproduce the star formation at high redshift. So, and then once you make the star forming galaxies, still there's another complication for Lyman-alpha emitters. Yes, Lyman-alpha is not simple tracers of the star formation. So this shows the recent, last project result. Looking at the redshift 0 Lyman-alpha emitters, well, they are close enough, so you can spatially resolve the distribution of stars and Lyman-alpha emission lines. And Lyman-alpha emission lines are shown with the blue colors here, and the others are continuum, and the red one is the H alpha. So as you can see, well, you have blobby structure of the Lyman-alpha, but with no stars here. And even around the center, you see some blue components together with the stellar components. So from the observations, Lyman-alpha emission comes from, there are two regions. One is the central interstellar medium regions, or within the stellar disk, or H2 regions. And the other is the circumgalactic medium that do not have much stars, many stars. So then I show another difficulty. Lyman-alpha emission line, sources. There are 5 major sources of the Lyman-alpha emission. Okay, so in 2 regions, as I said, central ISM regions and circumgalactic medium regions. So in the central regions, of course, the H2 regions emit the Lyman-alpha emission lines, and also the nuclear activities of AGN produce such Lyman-alpha photons, if any. And in the circumgalactic medium region, then so this central regions, basically the recombination produces the Lyman-alpha. And for circumgalactic regions, mainly they are collisional excitation, scattering, and the background radiation. So the third process is the outflowing gas, shock heating, and inflowing gas made by the cold accretion. By the cold accretion, gravitational energy is released, and then it makes the more collisional excitation to make the Lyman-alpha emission And also the fluorescence, if you have the strong UV radiation field nearby, like quasars or, well, strong, star-forming regions, then you get the fluorescence in Lyman-alpha in the regions outside or near to the surface of the galaxies, CGM. So, well, it is very complicated. And another complication is that Lyman-alpha is a resonance scattering line. So, if you observe Lyman-alpha, it is not, the Lyman-alpha velocity doesn't tell you the dynamics and positions of the Lyman-alpha source because they have a lot of scattering within the media. So as you see in this last galaxy, so a lot of the Lyman-alpha emissions coming from here. Of course, there may exist small H2 regions around the edge of the galaxies, but it's also possible that these Lyman-alpha emission is just simply scattered by the gas cloud, and the main source of the Lyman-alpha is confined within the interstellar medium. So, so it is very difficult and challenging. And so I would like to explain more detail in the lecture tomorrow. So this is the summary of the galaxy formation. Theoretically, I show the galaxy formation things, very basic ideas, what observers should know. And cosmic structure formation, it's okay, clear, but star formation is a problem. And another complication for Lyman-alpha emitters are the 5 sources of the Lyman-alpha emission mechanisms. So that also makes the things very complicated. So then how many minutes do I have? 0?
No, 15 minutes.
15 minutes, okay. So let me go through just spending 5 minutes for the observation component or next section, because I have a lot of material to complete, and I want to talk about more about the observations. So, well, let's look at the very, the first, easy thing of the Lyman-alpha emitters for observations. So the next section is the observations and the observed quantities, properties of the Lyman-alpha emitters, stellar population, luminosity function, morphology, ISM state, AGN activity, and hosting halo mass, and so on. So here, I just want to go through the stellar population thing, so for observations. So now we have the big telescopes, optical to the near infrared, even from the space. So having these big telescopes, Lyman-alpha emitters, spectral energy distributions are well measured. And this is the earliest measurement of the Lyman-alpha emitter SED for the redshift 3.1 LAEs. They are very faint, so the first Eric Geiser stacks the data and to get this average SED. And then he applies the stellar synthesis model, and then he found that the stellar mass of the Lyman-alpha emitters is as low as the 10 to the 9th solar mass. However, so several years later, so simple stellar synthesis model has a problem, especially for understanding Lyman-alpha emitters, because these Lyman-alpha emitters are producing strong nebular emission lines because they are low metal poor. So, and also, they are sitting at high redshift. So in other words, equivalent width of the nebular emission line gets large by a factor of 1 plus z. So, so this is the example of the redshift 6 galaxy shown by the Daniel Charest and Stéphane de Barros. And well observed photometry is shown with the red colors here. And if you use the simple stellar synthesis model, you obtain the very significant Balmer break here, But if you bring the nebular emission model, if you include the nebular emission that is given by the local galactic H2 region empirical relation. Then if you carry out such a model, shown with the black lines here, so then your continuum doesn't have the Balmer break, but a significant oxygen 3 and H alpha emission lines. And then you understand these two strong lines mimic the Balmer break. So this was suggested by this study. And if you do not include the nebula emission lines, you overpredict the mass and the age significantly, like the mass, stellar mass is overestimated by the factor of 3. So then people started to use the nebula emission line model with the stellar synthesis model. And then now we understand that the average Lyman-alpha emitters at redshift 2 to 7 have the stellar mass of 10 to the 7th to 10 to the 10th solar mass. Color excess is almost 0 to 0.2 for the peculiar sources, outlier sources, quite low extinction. And the star formation rate is just a few solar mass per year. And the age is 1 to 100 mega year or so. So this is the last slide of my lecture here. So this shows the very recent result of the Alex Hagan here. So this shows the star formation rate as a function of the stellar mass. And these gray and magenta points show the distribution, star formation main sequence of down to the 10 to the 10th solar mass given by photo Z selection or BZK selection and so on. So if you compare this with the other Lyman-alpha emitters shown with blue points, well, they follow near to following the extrapolation of the main sequence. Also, many of the Lyman-alpha emitters are coming to the a little bit upper side. In other words, they are showing the burst mode. So of course, you have strong Lyman-alpha emission, so you need the active star formation. So this is quite clear. So maybe Lyman-alpha emitters are populated and also quite representative of the low mass star forming galaxies and showing some of the starburst. Okay, so then, okay, time is limited, but how many minutes do I have? 10. Okay, 10 minutes. So it's your turn. So discussion, the presentation again. My question is, what is the most challenging component for modeling Lyman-alpha emitters and phi? Please start to discuss, and please choose another partner, which is who are different from the previous lecture. So if you talked with the left person, then right person. Please.